Introduction. I again want to thank you for taking the time to talking to us at EPFL. This is part of the CIS seminars where, for EPFL wide. I am part of the scientific committee, and it's really my great pleasure to introduce Professor Surya Ganguli from Stanford University. He is currently an associate professor of applied physics with several appointments in neurobiology, in EE and CS. He's also involved at Meta AI research. And his background is fascinating. He has majored in physics, mathematics, EE, CS, string theory, theoretical neuroscience, amazing topics, and he has been awarded many awards, and including NeurIPS Outstanding Paper, Sloan Fellowship, and NSF Career Award. Without further ado, and even before maybe starting, I want to share that I had the pleasure to listen to Surya in 2015 during the AI Salon at Stanford, where he actually talked about how to use neuroscience to build an AI. It was extremely fascinating, and I really look forward to hear your talk today. Thank you again, Surya.
Cool, thanks. Thanks for the kind introduction. Yeah, so it's great to talk to you, even though it's sort of so far away. But let's see. So yeah, so I was going to talk to you about sort of the interaction between sort of physics and AI today. So we do a lot of work in neuroscience. I work with experimental neurobiologists to understand what's going on in the brain and so forth. Here's some examples of some of the stuff that we've done, but I won't really talk about my neuroscience work so much today. I'm going to talk about sort of more of our AI work and why do I work in both neuroscience and AI? Well, I think there's an incredible room for an alliance between neuroscience, machine learning, and of course the mathematical and physical sciences for analyzing both systems. So, for example, we like to understand, what does it mean to understand a brain? A more proximal version of that is we like to understand how the connectivity and dynamics of the neural circuit give rise to behavior, and also, how do these systems learn? But, interestingly, now the field of machine learning has generated lots of learned neural networks that accomplish very interesting functions that we know of no other way of doing in any other artificial system at the moment. And what's really shocking is we know everything about them. We can do any experiment we want. We know their connectivity, their dynamics, their learning rule, their developmental experience. Yet we don't have a meaningful understanding of how they learn and work. So I think the desire to obtain such an understanding spans both neuroscience and machine learning. And also what's interesting is we can go beyond what evolution has given us, and we might want to try to exploit novel physics to implement neuromorphic computations at even lower power and higher speed. For example, maybe using photons instead of neurons or electrons. And I'll talk a little bit about that today. We outlined this kind of logic in an opinion piece a while ago. Okay, so here's, for example, a sampling of our works on just machine learning theories. So for example, this paper, this paper that we did a long time ago, sat in relative obscurity for a while, but then gave rise to these diffusion models, which I'm very happy to see have taken off. So there's actually a lot of room for using ideas from mathematics and statistics and physics to analyze these neural networks. I can't talk about all of this work. If you're interested, here's a review that we wrote in the annual reviews of condensed matter physics, but for hopefully a wide audience on lots of aspects of analyzing neural networks using ideas from physics and math. Here's a slightly older review on a unified approach to understanding a variety of topics using the statistical physics of disordered systems. And actually, I should say at EPFL, you have incredibly great resources, Lenka and Florent, who are really world leaders in this sort of interplay between statistical mechanics and computation. So I encourage you to talk to them. Okay, so what will I talk about? So I'll just talk about two vignettes. One is about the geometry of high-dimensional neural network error landscapes. We all care about this geometry because we want to navigate this geometry somehow to get to points of low error. So what do they look like? And in particular, can we systematically anneal, i.e. change them to aid optimization? And actually, I'll be looking at this question in the context of a specific error landscape that corresponds to a quantum optimizer that can actually be built in the lab. And we'll use statistical mechanics to understand their performance. And then the second part, I'll talk about some very recent work I did at Meta, actually, where we show how to beat power law neural scaling that's sort of governing how errors fall off with system size or amount of data. And this will connect some theory with experiments in machine learning and yield some engineering and performance improvements. Okay, so let's start on the first part. So I'll be talking about a machine called the Coherent Ising machine. I won't really go into the physics of it. But what they can do, what they can actually build in the lab is they can build up a system of interacting photons that can solve optimization problems. If you're interested, here's a review that I wrote with some colleagues. This is the work I'm going to talk about right now is joint work with a graduate student Atsushi Yamamura and an applied physics colleague of mine, Hideo Mabuchi, at Stanford. Okay, so here's the basic abstraction of the machine. Okay, so first of all, here's the Ising energy function, right? Where xi and are spins, they're plus or minus 1, and jij is the connection between them. And it turns out a host of combinatorial optimization problems can be mapped to an Ising energy minimization problem for some values of jij. You can think of the jijs as encoding a particular combinatorial optimization problem, okay? Minimizing this energy function for arbitrary jijs is an NP-hard problem. And but this is the problem we'd like to solve. This is a hard problem, so we might try to spectrally relax the problem. Instead of having the xi's be binary spins, we could just make them real numbers subject to a normalization condition. So the x lives in the unit sphere. And then minimizing this energy function with a minus sign is the same thing as computing the principal eigenvector of J, right? And then we could take the principal eigenvector of J and compute its signs and then get a guess for a solution to this problem, okay? This principal eigenvector solution isn't of the second problem is not always a good solution to the first problem. Okay, this is what the coherent Ising machine energy function looks like. It has a parameter A that corresponds physically to a laser power that you can pump into the system of photons. The x's correspond to the x quadrature of an optical parametric oscillator, which is basically the oscillating photon field. We don't need to worry too much about these physics details, but this x is a real number. You can just think of it that way in the classical limit, all right? And so every x has a potential, right? This individual site term. If A is negative, then this potential is just a quadratic looking potential, right? But if A becomes positive, this becomes a double well potential. And the photon quadrature likes to sit at a positive or a negative value in the absence of these interactions. Okay, and then you turn on the interactions, and if you crank up A, then this energy function essentially interpolates between the spectral energy function and the Ising energy function, because if the laser power is really large, the photons commit to either their positive or negative values. So it looks like the Ising system. Okay, so how do you use this so-called photonic computer? Well, what you do, we're going to analyze how it works for a specific ensemble of JIJs, just to choose the JIJs to be random and Gaussian. This corresponds to the famous Sherrington-Kirkpatrick spin glass. It's a hard optimization problem, but not one of the hardest ones out there. It's hard for simulated annealing, but there are message passing approaches that can solve this problem. We'd like to understand how a more general machine, the coherent Ising machine, the CIM, solves this particular problem. So the way you use the machine is you start the x's at the origin, it's so-called vacuum state of the photon field, and you start cranking up the laser power, okay? You increase the pump power a small amount, this parameter A, you minimize the energy via gradient descent, and you repeat, okay? And then how well does it work? Well, this is the Ising energy that the system finds, okay? For reference, this green horizontal line is the Ising energy found by the spectral solution, right? Just take the principal eigenvector, compute its signs, and then compute the Ising energy. This is what you'll get. This is the known ground state Ising energy of the Sherrington-Kirkpatrick spin glass. It's down here. And these blue points are what you get from the coherent Ising machine for an optimal annealing schedule, basically how you crank up the laser power A as a function of time. And this is the system size N. And as you can see, we get really close to the ground state Ising energy, and we're much lower energy than the spectral solution upper bound, okay? So this annealing schedule works really well. And so the questions we'd like to ask are, what makes this possible? What is the shape of the energy landscape as you crank up the laser power? And how can we exploit our understanding of this changing geometry to determine this optimal annealing schedule that led to these results, okay? Okay, so let me give you the take-home messages first. Let me give you a geometric picture of the landscape. So again, this is the energy landscape. We'd like to understand its shape over the domain X for a random Jij. Okay, so this is actually the picture. So you can ask, for example, in terms of the CIM energy and the radial distance from the origin in X space and the laser pump power A, where does the global minimum lie? It turns out the global minimum lies, of course, at very, very low energy and at a very large radius in X space. So these two dimensions are a stand-in for the n-dimensional X space, and this vertical axis is the energy. So the global minima lie at low energy and large radius. Where do the most likely local minima lie? It turns out they lie at a slightly larger energy and a slightly smaller radius. Then you can ask about saddle points. These are critical points where the gradient of the energy vanishes, but the Hessian may have negative curvature directions. And the index of the Hessian is the number of negative curvature directions. And so the index 1 saddles will lie at a higher energy and lower radius and so forth. And so you get this very, very complicated landscape riddled with saddle points of increasingly lower and lower index until you get to minima, and then eventually you get to a global minimum. Right? So if you were to start descending this landscape at large A, it would be a very difficult energy landscape to descend, okay, because of this geometric structure. Okay, also we can answer more than that. Given a critical point, either a minimum or a saddle point, what is the distribution of the OPO quadratures Xi? What does the photon field look like? And what is the entire eigenvalue spectrum of the Hessian of a critical point as a function of its index, energy, and radius? Okay. So now let me give you results to justify these take-home messages or this take-home message picture, okay? So what do we do? What are the theoretical ingredients? I won't go very much into detail at all, but what we do is we use something called the Catch-Rice formula that allows us to count critical points as a function of their energy, their index, and their location as the system size goes to infinity. We use the replica method to average over the random Jijs. And it turns out there's some supersymmetry tricks that we use as well. But again, I won't go into the details. I'll just tell you what the answers are. Okay, so here's the basic picture. How do we justify this conceptual picture on the right? Okay, so these are the results on the left. So what we did was, we did both numerics and analytic theory. For the numerics, what we did is for a relatively small system size, n equals 15, we used Newton's method to exhaustively search for all possible saddle points of any index and minima, right? And this blue-green heat map is a density of where we find all these critical points, right? We plotted them in a feature space where the horizontal axis is the energy with low energy over here, and the vertical axis is the radius, right? And so the global minima sit here, right? There's many random Jijs that led to this picture. So the global minima sit here at low energy and large radius. So that justifies this bottom circle. And as you go up in energy, you find higher and higher index fixed points, right? Now, what we did is these black points are the average location in this two-dimensional feature space of all critical points of a fixed index, right? So this is the low index ones, this is the higher index 1, index 2, and so forth. And this red line is what we predicted from an analytic theory through a combination of the Catch-Rice formula and the replica method. And you can see there's a really nice correspondence. So this tight correlation between the index of a critical point, its energy, and its radius justifies this take-home visualization of the energy landscape of this neural network, okay? All right, going beyond that, we can also compute the empirical histograms of Xi at any minimum and the Hessian eigenspectrum as a function of the laser power. So the blue are histograms for numerics, and the orange are plots of our analytic theory. And you can see a nice match between analytics and numerics. And intuitively, as you'd expect, as you crank up the laser power, the photons commit to either plus or minus values. But the Hessian eigenspectrum shows an interesting structure where there's many, many eigenvalues near the origin, right? And as you crank up the laser power, that doesn't change. The density goes down near the origin, but there's no gap in the spectrum. So what this means is for a typical local minima, if you just pick a local minimum at random, it will typically have a very flat, a large number of very flat directions, right? Corresponding to zero eigenvalues of the Hessian or close to zero eigenvalues. On the other hand, the global minimum shows a different structure. It commits much more deeply than the local minima. But the Hessian eigenspectrum undergoes a phase transition where there's a gap from the origin to the smallest eigenvalue. So basically what this means is there are no flat directions. Every direction is stiff and the curvature is positive or bounded away from zero. And this we call the freezing transition of the global minimum. At low laser power, the global minimum is just like a local minimum in the sense that there's no gap, okay? All right, so this starts to give us a picture of the phase diagram of this landscape. It turns out as you crank up the laser power, the energy landscape undergoes several transitions, right? Of course, when A is very negative, the only minimum is at the origin, right? And you know, and it's just a standard minimum with all positive eigenvalues of the Hessian. When A goes above -2, you get exponentially many local minima, but they all have very similar energy densities. The energy per spin is the same for all of them. And they're all marginally stable, i.e. they have a flat landscape where you have many, many eigenvalues near the origin of the Hessian. Okay. So that's like this kind of a picture for the energy landscape. Then as you crank up the laser power, what happens is the global minimum separates from the local minima, and there's a range of energies in which you see minima. A typical local minimum will be at the highest energy, but the global minimum will be slightly lower. So again, you have exponentially many local minima, most of them are marginally stable, and there's a range of energies, right? So now you start to get a complicated riddled landscape. And then as you crank up A beyond a certain value, you get freezing of the global minimum. So it's no longer flat. Every Hessian eigenvalue is positive, bounded away from zero, right? Now, okay, so what are these lines and dots? So these lines are analytic theory for the energy of the global minimum, the energy of the typical minima, and the energy of a typical critical point of any index. And you can see they all have the same energy up to this phase transition, and then they separate. And the black error bars show you sort of what we get from numerics. And there's a nice match between theory and numerics here. Okay, this actually tells us how to compute the optimal annealing schedule. It turns out when the global minimum freezes, it doesn't help you to anneal the laser power beyond that. So what you want to do is you want to anneal A slowly up until this freezing power, up until this freezing transition. And actually, if you anneal only up to the freezing transition and don't go past it, the speed of annealing doesn't matter. You can actually crank up the laser power relatively fast as long as you don't blow past this freezing transition. And that's exactly what allowed us to get this good behavior. So here's an example where this, again, this is now the laser power, and this is the CIM energy we achieve. The blue curve is the energy of the global minimum. It, of course, decreases as you crank up the laser power. The red curve is what we get from adiabatic annealing, i.e. we crank up the laser power, do gradient descent, crank up the laser power, do gradient descent. You can see that our annealing trajectory follows the trajectory of the global minimum. And for reference, here's the energy of a typical local minima. And you can see that annealing can break past the wall of exponentially many local minima and come down to the adiabatic annealing, come down to the global minimum limit. So basically, a take-home picture that you can keep in your head is that, if you were to just start minimizing at large A, you'd have to start from the origin and get past all this complicated structure and hopefully get to the global minimum. That's a hard problem. But if you start at small a, what's happening is this picture is unfolding or growing like a peeling onion, right? You start off with nothing at small a, you get a ring of global and local minima that all have the same energy, and then you go outward and outward. So and the annealing trajectory surfs the surface of this expanding onion, and it ends up at a good point, at the outermost point where you have the global minima, as you see here. So that's kind of a very, I think, a very simple conceptual picture of how deterministically annealing the shape of an energy landscape allows you, through energy minimization and annealing, to get to lower energies than you otherwise would without the annealing. Okay. All right. I just wanted to advertise another work that I've started hanging out a lot more with my colleagues in my department who do a lot of interesting atomic, molecular, and optical physics work. And I just want to advertise just one piece of work that was published relatively recently, where my colleagues can build an associative memory device, a hot field associative memory, out of a cavity quantum electrodynamic system. And I was just helping them analyze sort of the dynamics of the hot field associative memory and its classical limit that comes out of the natural quantum dynamics. And we could show that it yields a more efficient associative memory device than what the classical hot field dynamics would. And so this kind of I think is an interesting interplay between theoretical neuroscience and atomic, molecular, and optical physics, which was actually a really fun collaboration. Anyway, but I won't go into any details on this, but here's the paper. Okay, so let me now shift gears to the second part of my talk, which won't have any quantum in it, but will connect a little bit more to machine learning, a practical machine learning that's being done today. Okay, so, and this concerns how do we beat this power law neural scaling? Okay, so this is work that was just accepted at NeurIPS. This is the paper, and this is work done by Ben Sorsher and Robert Garros, who were interns at Meta with me and Ari Marcos, and also Shashank, who's a resident at Meta. And so this was, again, another fun collaboration. Okay, so what are neural scaling laws? So a lot of work has shown that error in neural networks tends to fall off as a power law with either the number of parameters, the number of data points, or the amount of compute, or some combination thereof. But the exponent of this power law is small. So advancing, a lot of people are really excited by these power laws, but I actually think that they're almost a negative result because these exponents are so small, advancing AI through scaling alone is going to be expensive and unsustainable, right? So here's an example of, say, language modeling with large transformers. A drop in cross-entropy loss from 3.4 nats to 2.8 nats requires 10x more training data, right? In the image domain, if you train large vision transformers, if you pre-train them with some amount of data, going from 1 billion data points and adding 2 billion more data points leads to a drop of only about 2 to 3% on ImageNet. So somehow with this extra 2 billion data points, you're getting a couple of percentage points, right? So just scaling up the data alone is not that sustainable, and it's extremely costly. Okay. All right, so we were curious about this. So let me give you the key ideas and take-home messages of this paper before I go into the details, okay? So, So basically the slow power law scaling of error with data set size, what it indicates is that training examples are actually highly redundant, okay? Therefore, we should be able to prune data sets to identify sparse subsets of non-redundant examples. And if we plot error as a function of the size of a pruned non-redundant data set, we might be able to beat power law scaling. That was the hope, okay? That hope actually bore out a bit. So we'll show analytically that we can do this in theory for perceptron learning in a student-teacher setting and at least achieve exponential scaling there. And then we show in practice how to beat power law scaling for ResNets trained on benchmark data sets like SVHN, CFAR10, and ImageNet, and also vision transformers pre-trained on ImageNet and fine-tuned on CFAR10. And then we perform a benchmarking study of 8 different pruning metrics, plus a new metric that we develop that's cheap and scalable given a pre-trained foundation model and doesn't require labels to compute. And our metric allows us, for example, to train on 75% of ImageNet without suffering any drop in accuracy. So this was motivated by some earlier work that I did with my student Manshij, Paul, and Carolina, not my student, she's at Google, Carolina Dizugate. And so what we did is we were looking at data pruning specifically, right? And so here's the basic result. What we want to do is we want to identify a subset of examples that we can train on. So the idea was, let's just train on all of the examples for some small number of epochs, maybe 20 epochs for CIFAR10. So train a ResNet on CIFAR10 for just 20 epochs, right? Then for each individual data pointer example, compute its L2 distance from the decision boundary in the output probability space, right? So examples with a small distance, they're close to the decision boundary, or they may be on the wrong side of the decision boundary. But these examples are by definition hard. They haven't been learned correctly in a small amount of time. I'm just using the words hard and easy to assign a conceptual name to just extrema of the L2 score. Okay, on the other hand, examples with large L2 scores, i.e. they have a large L2 distance from the decision boundary, are by definition, we call them easy because they're quickly learned in a very short amount of training time. Okay, we can sort all of the training examples by their L2 score. That's what we call a pruning metric. We can average these scores by training over a few short runs, say 10 or so. And then what we do is we prune the data by retaining only a fraction F of the hardest examples. So the idea is the easy examples are easy. We don't need to spend much time on them. Let's just choose the hardest examples, okay? Then we throw away these networks and we just start from scratch, but we keep only the hardest examples, and we train a new network from scratch on only the hardest examples. And we ask, using this method, how much can we remove from a data set before suffering any accuracy loss? Okay, so this is the amount of data set that we remove, and this is the final test accuracy. The blue line is the baseline where you train a ResNet on all of the data. The purple line is the baseline. And then this blue line is the L2 score, our L2 pruning method. And we find that we can drop down to about 50% of the data before we suffer any loss in accuracy. We even get slightly better performance if we don't prune as aggressively. Okay, so basically, roughly 50% of CIFAR10 is completely redundant. We can drop it and not suffer any loss. Okay, and it's about 25% on CIFAR100. Okay, so, but this of course raises a whole bunch of questions. Why does data pruning in this fashion even work? Why is keeping the hardest examples the right approach, or is it? Might there be a better approach? Can we develop a mathematical theory of data pruning? How does performance scale with pruned data set size? And how does data pruning scale to ImageNet scale? Can it work there? And do we need new metrics there? So these are the questions we kind of set out to answer. Okay, so we wanted to start with a mathematical theory of data pruning, basically in this sort of student-teacher perceptron setting. So we, whenever we're doing theory, we need a mathematical model for the data. So here's the generative process that generates the data in our theory. So we assume that there's a ground truth teacher perceptron. So it has a weight vector T in n-dimensional space. And so it has a decision boundary corresponding to this n-1 dimensional hyperplane, right? We pick random Gaussian inputs and isotropic Gaussian inputs in n-dimensional space. And if they're on this side of the decision boundary, we label them to be plus. If they're on this side of the decision boundary, we label them to be minus. So basically we pick random Gaussian X, dot it with the teacher vector, and take the sign to get the output label. Okay, so the teacher generates the output labels on random data. Now the data pruning strategy mirrors what we did in the deep learning and data diet paper, We train a probe student for maybe a short amount of time. So then the probe student will achieve some angle with the teacher, which we're going to keep arbitrary as a parameter, right? Then what we're going to do, just mirroring the previous work, we're going to keep the hardest data that has the smallest margins with respect to the decision boundary of the probe. So, this will be the hardest data point because it has the smallest distance. And this might be the easiest data point because it has the largest distance, okay? But we score all the data by the distance to the decision boundary. And then we keep some fraction of the hardest examples. And then we throw away the probe student. We just use it to prune the data. Then we train a max margin learner on the non-Gaussian prune data. It's non-Gaussian because we discarded some data. And we develop a theory in the usual high-dimensional statistics limit where the number of inputs, n, is going to infinity. The number of data points, p, is going to infinity. But the ratio of the number of data points to dimensions is order 1. And then another important parameter is the fraction of data points that we keep. So alpha total is the total data set size that we have to start with. And alpha prune is the pruned data set size that we have after we keep only a fraction f of the hardest examples. Okay, so that's the setup of the problem. Okay, so what kind of theoretical results can we get here? So here are the important parameters of the problem, right? So remember, we have three kind of perceptrons at play. We of course have the teacher perceptron that generates labels. We have the probe perceptron that's used to prune the data. Then we have the student perceptron that's trained from scratch on the non-Gaussian prune data set, okay? So a key parameter is the angle between the teacher and the probe, okay? And let's let Z be the projection of the data X onto the probe student. That's what we're using to prune the data. We're going to actually solve a slightly more general problem. We're just going to assume that the data has an arbitrary distribution P of Z along this probe student, right? And we're just going to assume it's some arbitrary non-Gaussian distribution. And then we'll assume the data is Gaussian along every direction perpendicular to the probe student's vector, weight vector. Let's let kappa be the margin of J student with respect to the training data. We're going to maximize kappa at the end of the day to get the max margin learner's performance. And then alpha total is the ratio of the total number of data points to parameters before pruning. Okay, now there's certain quantities which concentrate in the high dimensional statistics limit. For example, the cosine angle between the student and the probe, that will concentrate to a particular angle. The cosine angle between the student and the teacher will concentrate to a particular value. And of course, the angle between the student and the teacher determines the test error of the student. The test error is just the inverse cosine of the cosine angle, basically. Okay. Now, what we can do is we can analytically compute these concentrating quantities as a function of the problem parameters. And we get this set of equations, okay? You don't need to parse these equations, they're all in the paper. I just wanted to show them to show you that there's some meat behind this and that we can actually analytically compute the test error in an arbitrary setting like this, okay? So what do we get? Okay, so let's first analyze the setting where we have a perfect pruning metric so that J probe equals the teacher. So this angle theta is 0. So then what happens? Okay, so these are the results. Okay, so let's go through this a little bit slowly. So this horizontal axis is the number of training examples per parameter after data pruning, right? This is exactly the number of training examples that go into training the student, okay? But now for any given pruned data set size, there's a one parameter family of ways to achieve it, right? Because alpha prune is F, the fraction I keep, times alpha total, the amount I started with, right? So for example, to achieve a pruned data set size of 2, I could either start with a very large alpha total and do very aggressive pruning at small f, or I could start with an intermediate size alpha total and do a slightly larger f, like do less aggressive pruning at larger f. So for any given alpha prune, there's a family of curves, okay? Corresponding to this one parameter choice of f and alpha total subject to a fixed alpha prune. Okay, if I keep the total amount of data, f equals 1, that's like either doing no data pruning at all or just doing random pruning, okay? And so that's this black curve, and it's well known that this decays as a power law with exponent -1 for perceptron learning, But it turns out if I start with a larger data set size and prune more aggressively, I can do much, much better, right? So for example, if I keep 10% of the data, but start with a 10 times larger data set, I can do much better than if I just did random pruning. And so it turns out in this, for a fixed alpha prune, if you compute the Pareto optimal trade-off between F and alpha, that Pareto optimal curve actually falls off as an exponential, or at least faster than an exponential, and it's not a power law. So this shows you that there's a sequence of prune data set sizes where you can do much better than power law scaling with respect to the data set size, right? So also very interesting, if you don't start off much data to begin with and you prune by keeping the hardest examples, you actually do worse, it turns out, and I'll say more about that. Okay, so here are the take-home messages. At any fixed pruning strategy with a fixed F, as you increase alpha total and therefore alpha prune, eventually, so a fixed F is like a constant color curve, eventually you'll hit a power law, right? With the same exponent as no pruning, but you'll do better than no pruning. But if you find this Pareto optimal trade-off, you'll do better than a power law. And the strategy that allows you to achieve this Pareto optimal trade-off is, as you get larger and larger data sets, you prune more and more aggressively. Okay. All right, let's go back to this notion of keeping the hard versus the easy examples. So we analyzed that and we made a prediction. We don't need to go into all of the details, but the take-home message is, if you have a lot of examples to begin with, then keeping the hard examples is a good strategy. If you have few examples to begin with, then keeping the easy examples is actually a better strategy. Right? So this is a prediction that comes about from perceptron learning in the student-teacher setting, but it was such a striking qualitative prediction that we decided to test it in a much more general setting. For example, ResNet 18 on CFAR 10, and strikingly, we got exactly the prediction borne out, right? If you have lots of data, train only on the hard examples. If you have very little data, keep only the easy examples. Okay, so in the perceptron student setting, this is sort of the picture. If you have lots of examples, if you don't have that many examples, you want to keep data points with the strongest signal, i.e. that align most strongly with the teacher, so the north and south poles. But if you have lots and lots of examples, you want to keep stuff near the equator so you get detailed information about the teacher's decision boundary. That's the basic picture. We can actually compute the optimal distribution P of Z, but I'll skip those details now. By the way, I just wanted to advertise a slightly older paper where we also looked at learning with non-Gaussian distributions. And there we were able to find the optimal loss function and the optimal regularizer for high dimensional regression with non-Gaussian signal and noise. So if you're interested, there's this paper and there's related papers that we cite in the statistics literature that also work on this problem. Okay. And I'll skip that. Okay, now I've been talking about the situation where we have a perfect pruning metric, where J probe was equal to the teacher. But what if there's some finite angle between J probe and the teacher? Then what happens? So for reference, this is theta equals 0. This is theta equals 10. So what happens is ultimately all roads lead to power law scaling, right? But pruning data does better than not pruning data or pruning randomly still. But what happens is, because the imperfection of the pruning metric, eventually there's a minimum lower bound on how much you can prune down to, beyond which you won't be able to go further. So for example, with a 10-degree difference, you can't prune more than 24% of the data set. With a 20-degree difference, you can't prune more than 46% of the data set. Okay, so basically, with an imperfect pruning metric, this exponential decay eventually crosses over into power law decay. Higher quality pruning metrics delay this crossover. And for a given angle, keeping a fraction f of data less than f min of theta does not help. Okay, so the quality of your pruning metric matters. Okay. All right. Just the take-home message of this slide is that we can actually compute the information gain per example. And with no pruning, there's diminishing returns. The information gain vanishes. With pruning, the information gain can be finite. So the take-home message of this is you get slow power law scaling with respect to data set size because the data is redundant. But if you prune it intelligently, you can keep finite information gain per example and thereby achieve exponential decay of the test error with pruned training set size. Okay. All right, now let's shift to becoming a bit more practical. Can we test this prediction of at least beating power law scaling? Right, so for reference, here's the perceptron in the teacher-student setting. And then we trained a ResNet 18 on SVHN, on CFAR 10, and a ResNet 50 on ImageNet. These black curves are just what you normally do, right? Train on either randomly pruned data or unpruned data, which are, either one. And you get these exponents, you get this power law decay. And these exponents that we find are consistent with exponents that are previously reported in the literature for these problems. And then we do our pruning, okay? So, we can go from no pruning at the dark blue value to very aggressive pruning at the light green value. And you can start to see that you can beat power law scaling here. Now, in the perceptron setting, we had access to unlimited large amounts of data, so we could prune very aggressively. But for these finite sized data sets, we're limited by the total amount of data we start with. So we don't have access to large amounts of data that we can aggressively prune. So for example, this 1% line just stops here. Presumably, if we had more data, these lighter lines would fall lower below this curve, right? So that sort of remains to be tested, and we're working on that now with much larger data sets. But you can see in each of these cases, this power law is not an immutable law of scaling in computer science. It can be broken if you choose the data intelligently. Also, in the setting of transfer learning, for example, we can take a vision transformer pre-trained on all of ImageNet 21K and ask how much data do we need to fine-tune it on different pruned subsets of CFAR 10. And again, we can beat power law scaling there as well. So it works also for fine-tuning, not only for training from scratch. Okay. All right, so then because the quality of the pruning metric matters, we decided to look at a whole bunch of pruning metrics. I don't really have time to go into all of the details. It's not super important, but there's a whole bunch of scores, some used for pruning, some never before used for pruning, that tell you how hard or easy different examples are. That's kind of the take-home thing. There's a whole bunch of proposals out there. We benchmarked, but not all of these proposals have been uniformly benchmarked on ImageNet. So we benchmarked them on ImageNet. This is the fraction of data that we keep on ImageNet. This is the top 5 accuracy. This horizontal black line is the baseline where we don't drop any data. And you can see that all of these methods suffer a little bit, right? By the time you drop to 80% of the data, a lot of these methods suffer. There's 2 methods that do pretty well. One is something called memorization that's very expensive to perform and requires labels. And this light blue thing is a metric that we came up with that performs really, really well and is much cheaper to compute if you already have a pre-trained foundation model in your data set. Okay, so let me talk now about this new pruning metric that we came up with that outperforms all other metrics. And for the one that it matches, it's much more efficient. Okay, so what is this pruning idea? So again, we're following the idea of let's try to keep the non-redundant examples. So what we could do is, let's say that we have a data set to begin with, and let's say we don't even have, well, okay, let's say we have a data set with labels, okay? How might we want to prune it? Well, what we could do is we could start with the embedding space of a pre-trained foundation model, right? And then we could embed our data into the embedding space of this pre-trained foundation model. And because we have labels, we can compute class conditional centroids for each class in this embedding space. And then we can compute the distance of each data point to its own centroid. And we could keep the hardest, which is by definition the least prototypical or the most outlier data points, i.e. the data points that are furthest from their class centroids. And we could just train on those, and we keep some fraction of those and we titrate that fraction. Okay, what if we don't have labels? So that's the self-supervised prototypes. We could do the same as the above, except we use k-means, we use k-means clustering to determine the centroids. And this doesn't even require labels. So the basic algorithm is you throw your data into a foundation model, If you don't have labels, you just do k-means clustering and you keep the outliers, some fraction of outliers. Okay, and that's this light blue line here. And as you can see, it allows us to drop somewhere between 80 to 70% of ImageNet without really suffering a decrement in performance. Okay. We did we computed the Pearson correlation coefficient between all of these metrics. We find that there's sort of a cluster of metrics that are quite similar to each other. And our metric decorrelates from this cluster of supervised metrics. It's a different metric than those. We can look at the structure of how the clusters in the self-supervised embedding space map ImageNet clusters. There's a really nice structure where the self-supervised clusters often align with particular ImageNet clusters. So you can look for more details in this paper. But I think what's instructive is just going back to the data and trying to understand which data points are outliers and which are not, i.e. which are the hardest examples and which are the easiest examples. So sorry, to not cherry pick the data, we just looked at class 100, 200, and 300 in ImageNet. Class 100 happens to be a black swan. The top row are the easiest examples. And you can see that all of these black swans are just very similar. All these images are very similar to each other. The hardest ones, the ones furthest from their cluster centroid, are these images. And you can see that they're all idiosyncratic images of black swans, and each one is idiosyncratic in its own way. So you can imagine that if these images are quite redundant, you can probably drop some of them and not suffer any performance decrement. But these ones would be important to keep when you train. You can kind of tell yourself that as a just so story. Class 200, Tibetan Terrier, it's the same story. The easiest ones all look very similar. The hardest ones all look idiosyncratic in their own way. And the third, class 300, the tiger beetle, again, similar story. The easiest ones look very similar. The hardest ones are idiosyncratic in their own way. There's even a cartoon image of a tiger beetle. Like, I wonder who put that in there into ImageNet. These pruning metrics are also a great way to find all these weird examples. Okay, so just to summarize, we show analytically how and when we can beat power law scaling for perceptron learning in a student-teacher setting, at least achieving exponential scaling there. And we show in practice how to beat power law scaling for ResNets trained on SVHNs, CFAR10, and ImageNet. We perform a large-scale benchmarking study, and we develop a new metric. Okay, I wanted to kind of outline kind of a vision for the future, which is this notion of foundation data sets, right? So our current practice of ML, collect and train on large random data sets, as we can see, is highly inefficient and unsustainable due to slow power law scaling with data set size. The reason is in these large random data sets, most data is redundant. Perhaps we should invest in the search for and computation of good data pruning metrics that can identify so-called foundation data sets, which are high quality, non-redundant, small data sets capable of accurately training many different models. And the potential computational cost of finding foundation, finding foundation data sets could be amortized across the efficiency gains obtained in training many downstream models. And this is in direct analogy to how the computational cost of training foundation models can be amortized across the efficiency gains in fine-tuning them across many downstream tasks. So that's basically it. Our theory suggests that data pruning should be even more successful the larger the initial data set size. And so now we have many data sets that are approaching the size in the order of billions or sometimes even 1 trillion data points. Here's some now classic examples of very, very large data sets. Can we carve out of these data sets and disseminate much smaller foundation data sets out of them? That's an open question. And yeah, I'll just stop there and take questions. Thanks.
Thank you very much.
Oh, good. You're still there.
I'm still here.
I wasn't sure if I was talking to if the connection got lost or anything. Anyways, but yeah, go ahead.
So the Zoom is open for questions from the crowd. I believe that the audience can unmute, right, Maud? Or...
I know Amir has a question, but I just need to unmute him 1 sec.
Okay, I'm gonna unmute him. Yes.
Okay, I guess I'm unmuted. Can I, should I turn the camera on?
The camera
Somehow this time the Zoom felt like a big jail because I couldn't post questions. I guess others couldn't also. And then turning on the videos was also disabled. So, Surya.
Hey, Amir,
Oh,
good to
now
see you.
you can do it, I think.
Okay,
Yes.
great. Finally, out of the jail. Hi, Surya. Sorry, I was watching, but then I was behind the bars for permission. I actually have two quick questions. Both of them about the data pruning. The first piece that you showed, that actually, the first example of like training on, say, a small number of epochs, like 20 epochs and C410 or SDHN, and then using that as the criteria for selecting. So I lost connection for 2 minutes after that. So if the question was answered, I'm sorry in advance. But so don't you think there must be some sort of dynamic aspect to what determines a good or bad or hard and easy or useful, unuseful data point throughout the training of a neural network? There's a lot of like information theoric works that show that neural networks go through different phases during their training. So I found it like surprising that a fixed trained to a certain, I would assume like arbitrary number of epochs was actually a good identifier for throughout the training. Or you think it might not be the case, but since it's better than random, we are already seeing some light, but it could be still suboptimal.
Yeah, so we actually explored pretty extensively this hyperparameter of how long you train for before you prune, right? In the probe network, right? And it's consistent with other work that we've done where what happens is neural network training has a highly unstable kind of chaotic phase for the first few epochs, where a lot of things are very sensitive to choices that are made in the early training period, like which SGD mini batches you choose and so forth. But then after the first few epochs, things stabilize, like which basin you end up in is basically determined and so forth. So what we found is that as long as you prune, as long as you compute your pruning score after this initial chaotic transient, how much further you train for doesn't really matter that much. And so basically, there's a point of diminishing returns in how good your pruning score is as a function of how long you train. And that diminishing return sets in very early, corresponding to when the chaotic transient of training stops, which also stops very early.
I see. Interesting. Yeah, I guess I see. So then that's not contradictory, I guess, for those information theoretic analysis, because none of them have a notion of like an early chaotic phase that you mentioned. But I guess in your experience, you're saying that that early phase was not late, like too late to defeat the purpose of like
too late. Yeah. So we have a separate paper called Deep Learning versus Kernel Learning, and then some other stuff after it. If you look up that paper, you'll see a lot of extensive numerical experiments showing evidence for this early chaotic phase and its termination early in training, and the onset of a stable phase of training very early on.
I see, I understand. I'll look it up. And I also, if I can ask another question, Alex, is that okay? Or should we give this? Okay. The second question I had was, so when you are in the very aggressive data pruning, when you keep, let's say, 1% of the data, so how is that going to interact with the noise in the labeling of the data sets that we know are present? Like, coincidentally, we also have a paper in this coming NeurIPS on task discovery. It's basically, turns out there's a lot of competing like cues in one data set, say C400 or C410, many of the data sets that you have, that which one of them the network picks in order to do the same, give you the same classification and like a function of many things that go on. So we actually found, because we had an automatic method to actually find these competing cues, it turned out actually a good like number of the data points. I mean, well, it's not going to be a massive percentage, but they go through noise and it was known. So how does that work actually when you're in a very aggressive?
It's a great question. So in the deep learning and a data diet paper, we actually found that the quote unquote hardest examples that had the largest score were actually mislabeled examples. So you can imagine a slightly, and we did explore in that paper, a slightly larger space of pruning strategies that involve two thresholds, right? An upper threshold above which you drop data, and those are presumably the mislabeled examples, and a lower threshold, which is like the too easy data. The stuff below that is too easy. So you keep stuff in between these two thresholds. In this theory and experiment work, we didn't really explore that larger space of pruning strategies. We just said, keep a lower threshold and keep stuff above it. But you could potentially do better if you have lots of mislabeling. If you just add in that, and that just adds one parameter to your pruning strategy that you have to, one hyperparameter that you optimize over. But you're absolutely right. Our metric also picks up the mislabeled examples.
Yeah, what was surprising to me was that I would expect, so it's not the fault of your method that actually these errors exist, right? But that basically means when you use the top 10% of the data to do the same classification task versus top 1%, these are solving two different problems, right? One of them is going with mislabeling and the other one is not. So I was expecting to start seeing kind of contradictory trends when you go towards, very aggressive pruning, but it wasn't happening. And that's why I was like surprised that it's following the theory too closely.
Yeah. So what happens is at the 1% pruning, actually, we can see that figure now. The 1% pruning isn't, so 1%, it stops very early on and the error is quite high. So because
you're out of data, I guess.
You're out of data, right? Because we're starting with a finite size data set, right? To get way down here, you have to send, in the theory, you have to send alpha total to infinity and F to 0. Right? But we don't have the option of sending alpha total to infinity and F to 0 in these three examples, right? That's why right now, what we're working on at Meta are these types of data sets where, well, in particular with Lion that has like 400 million image text pairs or, 2 billion, depending on how, how you choose a subset of data. But, and so there we expect pruning, at least by our theory, to be, and intuition to be even more successful because you have more stuff to start with.
I see. Thank you. This answered the question.
Great. I hope that others can unmute themselves now if they want.
Yeah, now everyone can unmute themselves.
Awesome.
It's just suddenly sometimes during the talk, it's better to remove for everyone so then there's no accident.
So I don't see any unmute. Maybe I'll ask a question. So at one point we draw this conclusion that, given the amount of data, go for easy or hard example. Do you have recommendation or how to anticipate if we have enough data?
Yeah, it's a good question. One of the things we're thinking of working on is generalizing our theory to multi-class classification, like we just did perceptron classification with 2 classes. Because I think what will happen is the number of classes will play a role, at least in a classification setting. And so in the perceptron setting, we know the answer from our theory, right? Sorry, let me go to here. Yeah, so, this is the random pruning. So this axis is also alpha total. And so this tells you if you increase alpha total and decrease F, this is how much better you'll do, right? So basically, as soon as alpha total is bigger than 3 or 4, like you have 4 times the amount of data, there's parameters, you can potentially start doing better. That will be somewhere around here but we're not quite sure how the number of classes interacts with this because we don't have a theory for that yet. So the short answer is I can't really tell you. The practical answer, and the one we're following at Meta right now, is we just try it, right? We have a pruning strategy. We can compare it to random pruning. So what you do is you have a very large data set, say 400 million image text pairs. You randomly prune a subset to get an alpha total. You do your pruning algorithm on that to get an alpha prune, and you just explore the space and see how well you do. Yeah, you need a lot of compute for that, for this initial exploration, but once you sort that out, you can hopefully get some. So you take a very engineering approach to it as opposed to a theoretical physics approach to it.
Of course, thanks. And maybe a follow-up. In your vision, you suggested to have this predefined data set that have no redundancy. But so do you believe that they are not dependent on the learning framework architecture?
Yeah, so, okay, so that's an interesting question. So we also did some transfer studies where the probe student had a different architecture from the actual student that we trained. Like, so for example, the dream would be just train a really small network for a short amount of time, use that to get the scores, and then use that prune data set to train a bigger network. And we found that worked, you know, subject to some lower bound on the complexity of the probe network. So you can transfer pruning scores computed on one architecture to other architectures you're trained using data pruned using those pruning scores from a different architecture, right? So, but you know, that's still an empirical question, right? We need to test it in more settings and see what happens. But our initial transfer of pruning score metrics kind of worked.
But when you say different architecture, you're talking like adding layers, or for instance, we have convolutional neural network and we have like this vision transformer network that
Yeah,
are
so
really...
that's a good question. So we haven't done, so there was different layers, right? So can you
different
for
layer?
example,
okay, but it's
yeah.
not a...
Yeah. So I don't remember if we tried the experiment of CNN to vision transformer. We can try that again if we didn't do it already and see that. Yeah, neither of these two papers really focused on transfer of the pruning.
Right.
But I suspected, you know, we should try that. That's a really good question. CNN to vision transformer, would that transfer?
By transfer pruning, you mean transfer like if you have a pre-trained probe, or whether the trends would...
Yeah, so what I mean by that is you compute the pruning scores using one architecture and you select the data, but you train another architecture on that sub-selected data set.
Exactly. Yeah.
I suspect it won't transfer, but
then this paradigm of I'm giving you this prune data set.
Yeah. So I can tell you in the experiments that we looked at the transfer, it worked, but you're right, like we should do more experiments along those lines. The intuition for that is the following. I think it's more the geometry of the data that determines difficulty. For example, if there are data points from an opposite class close to many data points from another class, right? Then regardless of the architecture, that will be a hard data point. So
the proximity depends on your embedding, right? It depends on your strategy of how you...
It depends on the embedding.
So it depends on your everything, right? So
that's
you
true.
you're committing to a strategy for embedding, and then yes, but maybe I'll commit to a different strategy.
Yeah. There's no theoretical reason to believe the transfer will work. I completely agree. The few times we tried it empirically, it did work, but you're absolutely right. Like that's an extremely important thing to explore.
I mean, I can send you a pointer, Surya, for an experimental work. And this is not exactly on a transfer, but more like, let's say if you could define an optimal label set for a given architecture. Let's say this is the label set that is easiest to learn for network and easiest to generalize. So it turns out that this optimal set, I mean, which I don't get into how, but let's say if we could define it, is not the same for two different architectures, which is completely independent of the data, like on the same image set, but it's just a matter of even labeling. So if you extend that, is like the images are set, but only the labels matter. But if the label set that one find easy, you can extend it, transferring is basically learning from not Gaussian initialization. But I mean, who knows? But I'll send you the reference.
That's very interesting. Actually, it relates to some other work that we're doing, which I'm happy to tell you about. But how natural are these? So you're kind of now optimizing the labels for some architecture. So how natural, I mean, I don't know how to define natural, but you kind of get the question.
I guess interpretable. What do you mean?
Yeah, interpretable. Or how idiosyncratic are these data? In some sense, are the data sets overfit to the architecture?
Yes.
Right.
That's true. It's a very, I think, interesting empirical lens to understanding deep learning in this case. When you look at the labels, they don't look natural, I would say, interpretable. But the thing is, does it matter to be interpretable or not? Because this is not fitting to the training data set regime anymore. It includes generalization. So let's say if I have a task which I can train a neural network on, and it perfectly generalizes to unseen data, but I have no idea what this task is. It's more like my problem, which is like a human interpretability of it, because I can look at the images and the label set, and I think there's also some constructed examples in which you actually embed a statistical signature in the data that gives rise, makes it possible. Like, let's say third pixel from left and top is always like, if it's blue, I'm going to call class A. If it's red, class B, right? It makes it perfectly statistically learnable and generalizable. You train a neural network on it, it actually learns to do it. And what is more impressive is that it actually learns this very particular signature. Doesn't pick up on some correlating cue, because when you mess with that exact pixel, it starts kind of giving you the wrong results when you keep it and mess with everything else. But then you show to humans, of course can't understand this, right? Because we are unguided when we look at it. So I gave up on interpretability of it, and I kind of sided with generalization being a more meaningful, extendable.
So yeah, we should definitely exchange papers, because we're working on a problem of meta learning the data. Like, for example, we always look at our learning curves and we stare at them nervously and hope they go down quickly with time. And if they don't, we fiddle with the hyperparameters and whatnot. So what we said was, can we find data sets, both optimizing the labels and the inputs, so that the learning curve is very slow, for example, for a CNN, but very fast for a vision transformer, or vice versa. Or so for any pair of architectures, amongst MLP, vision transformer, or CNN, we find a data set that completely separates the two. And we're actually trying to understand the structure of these data sets. So we call them extremal data sets. We have no idea if they're natural or not, but there exist data sets that are hard for any architecture and easy for another. And I think they're very different from the data sets we usually think about, but insights into these extremal data sets will give us insights into the connection between the structure of data and learning curves and architecture, which I think is the fundamental open question one of the fundamental open questions of deep learning. So, in statistical physics, you take random data, right? So, but
I feel we can continue for hours, but I need
definitely. I wish.
Thank you so
Switzerland
much.
is far. It would have been fun to visit all of you, but I have a little daughter at home, 7-year-old daughter, so I can't travel that much. Anyways,
Again, thank you. Thank you everyone for attending the talk. This will be online. All the best.